All right, guys, we jump into section 11.2, really our first conic section here, ellipses. So we're going to give you the generalized definition of ellipses, just like we talked about circles, a set of points. So an ellipse is a set of all points that are a fixed combined distance from two fixed points in space. And we call those the focal points, or the foci, meaning one would be a focus, multiple would be a foci, also known as the focal points. Okay, so when we create this graph, we'll do a little bit, and then we have videos to show you a little visual definition that matches with what we just wrote down. Where a circle was a set of points that were a fixed distance from one point in space, and then we put a point down, go a certain distance, it would create a circle. Here we would have 2 points in space, and the combined distance from these points to every point along this ellipse would happen to be the same if you added them together. Okay? Now, we have 2 different types of ellipses, I guess. We have an ellipse that is wider than it is vertical, so more horizontal than it is tall. That would be this one. We would consider this one having a horizontal major axis. All right, that just means it is wider than it is tall. It is further apart horizontally than vertically. And then we have one that has a vertical major axis, taller than it is wide. Same thing, obviously, if the horizontal is the major axis, the minor axis would be vertical here, and vice versa for this ellipse. Okay. Sometimes we put like dashed lines here. We can do that here. This would be our major axis. This would be our major axis. It's important because the focal points will always fall on the major axis. Okay, the ones that we were talking about here, also known as the foci. We'll get to that momentarily. Now, the standard equation for an ellipse is very similar to that of a circle. Okay, you'll see some similar things. All right, so we'll start with x minus h squared. We'll have a big plus sign here, y minus k squared. All right, but these are both going to have denominators underneath them. And we're going to label them as r sub x squared and r sub y squared. Basically, the r sub x would be the number underneath the x that's on top, r sub y. Then it's always going to be equal to 1. Okay? All right. Now, same thing for this equation, x minus h squared over r sub x squared plus y minus k squared over r sub y squared equals 1. These will be numbers. These will be numbers. We'll always have the x and the y. Okay? Now, very simply, and we're going to use some different colors to denote different things here. All right, so in black, we're going to plot the center. All right, the center of an ellipse is literally what you would think. It's along the major axis. It actually happens to be along the minor axis too. Okay, it is in the center of the ellipse. Okay, halfway between what we're going to call the vertices. Okay, and the center, just like the center of a circle, in its general equation, is very simply h comma k. That's going to be exactly the same no matter whether we have a horizontal major axis or a vertical major axis. So let's kind of just estimate here the center of these ellipses would be at the point h comma k. All right. Now take note that there are minuses in the general equation, so obviously we're kind of thinking opposite of the sign. All right. If there is no h or k value and we just have x squared and y squared on top, obviously the center would be at 0, 0. Okay? The vertices, we're going to write those in red. The vertices are always along the major axis. Okay? All right, and the vertices are going to be here and here. basically the endpoints of the major axis, you'll find the vertices. Okay? So we're going to make those in red here. Okay? Now this is where the numbers underneath the in the denominator come into play. Okay? If there's a horizontal major axis, then the number r sub x is the distance from the center to the vertices, which means the vertices will be located at h plus or minus r sub x, comma k. If it is a vertical major axis, then the number underneath the y would be the distance from it to the vertices, from the center to the vertices. So r sub y would be the distance from the center to the vertices. It should make sense since we have a major axis that is vertical. Okay? So it would be h comma k plus or minus r sub y. And those would be the coordinates of the vertices. Okay? And we also have co-vertices. The co-vertices, okay, are the endpoints of the minor axis. Okay? So in this first one, endpoints of the minor axis. In the first, they would be directly above and below the center. In the second one, they would be directly horizontal or left and right of the center. And those would represent our co-vertices. And that's where the minor number under the denominator would come into play. So for this first one, the horizontal is the distance from the center to the major axis vertices, or just the vertices. The number under the y, so r sub y in this case, is the distance from the center to the co-vertices. That would be at h comma k plus or minus r sub y. And here, the number under the x, since the x's or the horizontal is the minor axis in this case, is the distance from the center to the co-vertices. So this would be h plus or minus r sub x, comma k. All right. And this is basically what we have here. Okay. All right, guys, there are two more points, or one set of points that become important in an ellipse, and it goes back to the definitions. The focal points, the points from the two from which every point around the ellipse or on the ellipse would be the same combined distance from those 2 points. Okay? We call those the foci. Singular would be focus. I know it seems like it should be foci, but it's not. Foci. All right? And the foci will be located along the major axis, equidistant from the center. So just bear with me as I put the focus on here. We'll call this like F1 and F2, the first and the second focus. Same thing here. It would be somewhere along the major axis, equidistant from the center. Okay? That distance from the center to the foci, or to one focus, that would be r sub f. That makes sense. If we're talking about the distances here. Okay? How do we calculate that? Well, we theoretically use the Pythagorean theorem. Okay? I'm not going to draw it on here, but I guess I can draw it on here. This distance is r sub y. We have r sub f. We have a right angle here. And this is actually the same as r sub x. Okay, this distance from the center to the vertex is the same as from the focus to the co-vertex. You don't really need to know that, okay? But I just want to show you where this formula that we're going to write down is about to come from. So the foci, using the Pythagorean theorem, sorry, that squared shouldn't be here. It should be on both of those. My apologies. Okay, so it's just the Pythagorean theorem. All right. There's absolute value bars here, so we don't have to rewrite it and figure out which of these would end up being larger. Okay. And that's how you would find the focus. So the focus would be at the point, all right, on the horizontal major axis would be h plus or minus the distance of the focus, comma k. Same equation here. Absolute value. Put that in there. There we go. And this distance, h comma k plus or minus r sub f. So r sub f is the distance from center to the foci. R sub f is the distance from the center to the foci. All right, so I would like to, before we talk about eccentricity, I'd like to just recap here, okay? Most of these notes is important that you understand the vocabulary, okay? So we have two different types of ellipses. We have an ellipse that is wider than it is tall, meaning the horizontal axis would be our major axis and the vertical the minor. Or we have one that's taller than it is wide. The vertical would be the major axis and the horizontal the minor, okay? The center, here's our standard equation, the center at h comma k. All right, the vertices will always be along the major axis, okay? The co-vertices will be along the minor axis, directly either up and down or left and right from the center, depending on which one's minor. And then the foci, all right, we will do a little bit of mathematical work, hearkening back to our Pythagorean theorem here. That would allow us to find the distance from the center to the foci, okay, or to each focus. All right, and the foci of every ellipse will always be along the major axis. Okay, so if it's a horizontal major axis, you'll find the foci to the left and the right of the center. If it's a vertical major axis, you'll find the foci above and below the center. All right. Lastly, we'll talk about eccentricity, all right, and get all of the vocabulary about ellipses will be done at this point, all right? And the eccentricity is really how squished is this oval, or is this ellipse, if that makes sense. All right, how squished is it? Is it fairly wide, or is it really, really narrow, okay? And the way we determine that is with a little ratio. The eccentricity is the ratio of the distance from the center to the foci over the distance from the center to the vertex. Or in this case, r sub y. And it's just a ratio. Okay? And the eccentricity is how squished is the ellipse. It's not something we talk about a whole lot, but it is part of our notes in our textbook. We don't traditionally assess or put eccentricity on quizzes or tests, but there is a nice connection that we'll make in an activity this week from eccentricity to things that we've learned in the past. All right. Again, most important part of all these notes is just simply understanding the vocabulary about ellipses and where these vocabularies can be found. Okay, so standard equation. How do I find the center? What's the definition of a vertex? Oh, it's always along the major axis. How would I find that? Well, it would be one of these parts of the standard equation would give me the distance from the center to that. Same as the co-vertices We do a little math to find the distance from the center to the foci, and we'd be able to plot them.